So the third topic in engineering physics is about fluid dynamics. Fluids are anything that flow, and we typically think of fluids like water, but air is also a fluid because it can flow. So the two most common fluids that we do physics with are water and air. Now there are other types of fluids like oil and things like that, but water and air are what we're going to focus on. So here's the equations, and what I'm going to do is kind of walk you through what each equation is and how it's used. So the first equation is buoyancy force. Buoyancy force, you can label it as FB or just B for short. So this is based off of Archimedes' principle. So here's what Archimedes' principle says. Let's say I have a container full of water, not full of water, but just water in this container. And I put something in the container, and when I do that, it's going to increase the water level. And there's going to be, this is like a rock or something I threw in the container. Now, the forces acting on the rock, there's gravity that pulled it down, but then there's buoyancy force. It actually made the rock a little bit lighter. It'd be easier to lift the rock in water than it is to lift it out of water. So there's a buoyancy force that pushes it up. And it displaced the water level went up. Now, here's what Archimedes' principle says. It says that the amount of water here, the weight of this water, is equal to the buoyancy force. The amount of upward force that the water is pushing up on this rock is equal to the weight of the water. So if I look at that equation up there, it says the buoyancy force is equal to the weight of the water, or the mass of the water, mass of the fluid, times gravity. Well, another way to write that, because density, this over density is rho, density is mass over volume. So if I multiply both sides by volume, then I would have that the mass of the water is equal to the density of water times the volume of water, the amount of water displaced. So that makes sense. The more force I put into it, the more it's going to displace the water. So, very good. So here's the first equation. The next equation is Pascal's principle, dealing with pressure. So if I look at this container again, it's probably common knowledge that if I jump into like a pool of water, the deeper I go into the pool of water, the higher the pressure is of water on my body. And it's because there's an equation for it. The depth of the water, and the deeper I go, the higher the pressure. So if I'm right here, there's a higher pressure than if I'm right here. So how do I calculate the pressure of any location in the water? Well, here's the equation for it. The amount of pressure is equal to this pressure, like the pressure up here, because this is also pushing the air pressure, atmospheric pressure is pushing on me. Because if I was at this level, right on the top of the water, I would still feel atmospheric pressure pushing down on me. But then I also want to add the pressure of the water, because the deeper I go, there's also water pressure, added pressure to it. So I'm going to add that pressure to it, and the equation is equal to the density of water, or any fluid, but focusing on water here, times gravity, times the depth. So as the depth goes up, the pressure goes up. Next is AV equals constant. What that means is based off of flow rate. AV is area times velocity. So here's an example. If I have like a river or something, and this also applies to like electricity. If I have a river that starts off wide and gets narrow, this is like the current, the flow rate, the current of the river. The amount of water that flows in has to equal the amount of water that flows out. And that's because of conservation of mass, essentially, because if more water flowed in than out, it would pool up, and if more water flowed out, then there'd be nothing left. So it has to have a constant flow. So basically, the way to write this equation, since AV is constant, you can say that like A1 V1, the one area of this river times the velocity of the river, is equal to A2 V2. So the current flowing in equals the current flowing out. So if this river gets narrower, the velocity gets faster. Or if it went this way, as it gets wider, the current's going to stay the same, but the velocity is going to be lower. Don't get velocity and current mixed up. Current is the amount of water flowing, Velocity is the speed at which it's flowing. A lot of people get this mixed up. The next one is Bernoulli's principle. And Bernoulli's principle, it can be expanded to a long equation, which they have written down here, but it can also be simplified to an easier equation. So here's what Bernoulli's principle says. It says that fluids, when they start moving fast, they spread out more, thus lowering the pressure. So the way to calculate that pressure, or change in pressure, is equal to 1/2 times the density of the fluid times the velocity of the fluid squared. This is based off of kinetic energy. It's saying essentially like that like work or kinetic energy is 1/2 mv squared. And if you remember, work is force times distance, 1/2 mv squared. If I divide both sides by volume, I have mass over volume, which is density. So I have 1/2 density squared. And then force times distance over volume. Distance over volume is 1 over area. Force over area is pressure. So that's where it's coming from. It's based off conservation of energy. It's saying that it's just based off kinetic energy. The faster something's moving, the more work you can do on it. Thus, the faster the fluids are moving, they spread out more, lowering the pressure. So this is the result of why planes can fly. They fly and they produce lower pressure above the wings and higher pressure below the wings, which produce lift. So we'll do an example of that in a bit. So they write the equation like this: 1/2 mv squared plus this, which is usually 0. This is like the thickness, or essentially the density times gravity times depth, how deep you are. That's usually just 0 because like the thickness of a plane is pretty small. Plus the pressure is a constant, meaning that the change in pressure is going to equal the change in your kinetic energy, or density, replacing mass with density. The next one is about drag force. Now, there's actually 2 equations for drag force. I'm going to derive one for you later, but there's another one that talks about viscosity. So here's the example. So if I take like a substance, and let's say there's some fluid in here. Let's just say it's like oil or honey, something really viscous, and I drop something into it, like a marble. So the marble is going to go into that fluid, and it's not going to fall at not 0.1 meters per second per second. It's going to be slowed down because there's a drag force. It's going to reach like a constant velocity because the fluid is like acting like a frictional force. So what is that frictional force equal to? Well, it's equal to gravity because it's going to go at a constant velocity, but it's also equal to that over there. It's equal to 6 pi. It's based off of the shape of the object, but 6 pi, if you're thinking of a circular object, times this. This is viscosity. This measures like the stickiness of the fluid, or like the frictional force inside the fluid, like between the particles of the fluid. And this is actually measured in Pascal seconds. It's a weird unit. And usually these numbers are pretty small. For like water, it's like 0.001. For air, it's like 0.000001, something like that. Times the radius, so the size of this object again. Times the velocity, how fast it's moving. So this is like your terminal velocity. So there's the equation for that. And the last thing is Reynolds number, R. Reynolds number measures turbulence. Turbulence is like the chaotic nature of how fluids flow. So if something's really, really smooth and calm, we call that laminar flow. If something's really chaotic and moving really fast, we call it turbulent. And think about airplanes. A lot of times they say there's a lot of turbulence in the air. So there's a lot of bumpy road, like a bumpy road, a bumpy airline as you're flying, because it's the chaotic flow of nature. You don't want that. You want a nice laminar flow on an airplane. But there's nothing wrong with turbulence. It's just that Reynolds number measures turbulence. So R is called Reynolds number, but basically just a number. There's no units on it. It's measuring turbulence. The higher the number, the more turbulent it is. So it's equal to the velocity. So faster moving fluid is more turbulent. That makes sense. Think about like rapids. Like if you're in a river or something, the rapids is moving faster, it's more turbulent. It's also equal to the radius. So since it's moving really fast and it's really wide, it's going to be more turbulent. It's equal to density. So more dense is going to have more kind of like more collisions. Like air is not going to collide with itself as much as something like fast moving water because there's a lot more collisions. And then divided by viscosity. Because those intermolecular frictional forces there. So that just gives you a straight up number. Whatever that number is, the higher the number, the more turbulent it is. Let's do some examples. Oh, and the last one up, let's do a density, mass over volume, pressure, force over area, which I'll review from previous topics. So let's use our first example. Let's go back to the rock example. Let's say I have a 10,000 Newton rock. It's really, really heavy. And its volume is 0.5 cubic meters. So that's actually pretty big. That's like just big around, a big rock. Really, really heavy. If I tried to lift that rock by itself, how much force would it take? It would take 10,000 newtons, which is just kind of an estimation. It's like a ton, 2,000 pounds. So this rock weighs a ton. It would take a ton of force, literally, to lift it up. But if I put it underwater, how much force would it take then? The water's going to make it easier to lift because the water's going to push up on it because of Archimedes' principle. But how much easier? Well, to think about it, we need to think about the forces acting on the rock. There's obviously gravity going down. Then there's buoyancy force. Well, there's me lifting it up, my applied force. But buoyancy force is also pushing it up, so I don't need to apply as much force. So my applied force would equal gravity minus my buoyancy force, FB or B for short. So let's figure out what these numbers are. My applied force is what we're looking for. That equals gravity, which is 10,000 newtons. So if there's no buoyancy force, that's how much force I would need, minus my buoyancy force. Well, how do I find my buoyancy force? I need to know the density of the fluid that it's in, water, which is 1,000 kilograms per cubic meter, density of water, times the volume of water displaced. Well, if the rock's in there, its volume is 0.5, which means the water volume is going to go up by 0.5 because you can't, where would the extra space go? Or if it was not that, if it was more than that, where'd the extra space come from? If it was less than that, where'd the extra space go? It has to be the same volume. So the volume of the rock is going to equal the volume of the fluid. So 0.5, because it's underneath the that's going to be cubic meters. So the cubic meters cancel out, so we're left with kilograms times, 9.1 mg, mass times kilograms, 9.1 times g, is the force of buoyancy force there. So literally I can just put that in my calculator, 10,000 minus this mess, I don't know. So 10,000 minus, let's actually just do this calculation first. 1,000 times 0.5 times 9.81. So the buoyancy force is 4,905 newtons. So I take 10,000 minus that, 10,000 minus 4,905, and I get a little over 5,000 newtons, 5,095 newtons. So what was once 10,000 newtons of force to lift, now it's only 5,000 newtons of force to lift underwater. It's still a lot of force, but it's you don't have as much, so it's made it easier. Another cool application of fluid dynamics is like flight. It's taking something and making it fly into the air. It's really cool. So here's an example of an airplane. So we have a 50 square meter airplane. It's the area. It has a mass of 100,000 kilograms. It's flying into the air at a constant speed, and it's able to stay in the air without falling. So that's kind of crazy to think about. So we're going to answer 3 questions here. So first of all, we're going to draw a free Y diagram to think about the forces acting on the airplane. Then we're going to calculate the pressure difference because obviously it's the pressure of the air around the plane is causing it to stay in the air, not fall. And then figure out how fast does this plane actually have to travel, the minimum speed for it to actually travel for it to stay in the air. Because if it slows down, it's not going to have enough speed to produce enough force to stay in the air. So let's start the free body diagram. So I'm just going to draw a box. Obviously, there's gravity pulling it down. We can actually calculate what that gravitational force is. It's 100,000 times 9.81. So that's 981,000 newtons of force pulling it down. But since the plane is not falling down, there has to be this upward force of lift that's also equal to 981,000 newtons of force. The force is an applied force, like a thrust moving it forward, Fa. And then there's drag force acting against it. Now, if it's moving at a constant velocity, we know the applied force and drag force have to equal each other. Now, Bernoulli's principle is kind of cool. One thing that Bernoulli's principle says is that the drag force is going to equal your lift force if it's moving at a constant velocity. So that means all these forces are actually 981,000 newtons. That's kind of cool. So there's our free body diagram. B, calculate the pressure difference of this plane. Well, we actually have a couple of equations for pressure, but the one that we're focusing on is this one, because this one is based off of the depth of something under a fluid, and we don't know that for this plane. We don't know any of that. We maybe know atmospheric pressure, but we don't know how high the plane is up, and plus this is not relevant to the problem. We're looking for the pressure difference, so that's going to be that. So we have P equals 1/2 density, which we know. Velocity we don't know. Ruh-roh. Wait, there's another way to figure out pressure difference. We can go back to our thermodynamic stuff and say pressure is force over area. So pressure is force over area. That's the same. We're still solving for pressure. We know the amount of force. It's 981,000. And we know the area. It's 50 square meters. Because pressure is force over area. So I divide those two numbers, I get 19,620. So this is 19,620 newtons per square meter, or pascals. Boom. That's how much pressure is required to cause, air pressure is required to cause this plane to fly. Well, now we can use that equation to figure out the minimum speed it needs. So it'll be 19620 equals 1/2. The density of air is 1 kilogram per cubic meter. That's no way to say that. That would write that unit, kilogram per cubic meter. So air is 1. And then V squared. So I multiply both sides by 2, divide by 1, square root it. I get that the plane has to fly about 198 meters per second. That's not a way to say meters per second. I missed the -1. Which is actually pretty relevant. That's actually pretty consistent. That's about 500 miles an hour. So that's how fast the plane needs to fly in order to stay in the air. If it starts to slow down, it's going to start to fall. And if it speeds up, it can actually produce even more lift. So next time you're on a plane, look at how fast it's traveling. You can actually you can work backwards to figure out how much the plane weighs or how big the plane is. So it's kind of cool. All right, the last example we're going to go through is like a draining tank. We have a tank that has some water in it, 1 meter deep, and there's a little small hole at the tank, so the water is able to drain out of this tank out of that hole. Now here's some measurements. It's 1 meter tall, or 1 meter of water above the level of the hole. The density of water is 1,000, and the hole has a surface area of 0.001 square meters. Now, it's a little circular hole, so I found the radius of the hole using area equals pi r squared. So the radius of the hole equals 0.001 equals pi r squared, divided by pi square root it. The radius is 0.018 meters, so about 2 centimeters for the radius of the hole. So pretty small hole, maybe about that big, or a pretty big tank. So we want to figure out some stuff about the tank. So we want to find out the initial pressure. Let's start with that. Well, the initial pressure, let's ignore this atmospheric pressure. Let's ignore it. Just say it's 0. In reality, it's like 100,000 pascals. That's not 0 at all. But we're ignoring it. We're trying to figure out just the pressure of the water. So what's the pressure of the water going to equal? Well, it's going to equal 0 plus the density of fluid. which is 1,000, times 9.81, that's G, times 1 meter deep. So this is just a 9,810 pascals. That's the pressure. Now I want to find the initial velocity. How fast is this water coming out? Well, it's going to slow down over time because the pressure decreases over time. But initially, it's going to have a lot of velocity coming out. Well, I want to find out velocity. Well, I know the pressure. I know the density. I can use this equation right here to find the initial velocity. So the change in pressure, because the final pressure is 0, so the initial pressure is 9,810. So 9,810 is equal to 1/2 times the density times v squared. Well, I would multiply by 2, divide both sides by 1,000, square root it. The velocity coming out is 4.43 meters per second. So that's how fast the water is coming out of the hole. And then as time goes on, the depth gets lower, the pressure gets lower, so the velocity goes down. What's the initial flow rate? Flow rate is measured in either cubic meters per second or kilograms per second. This equation right here, A times V, will give me cubic meters per second if I multiply by the area and velocity. So now the area of the hole times its velocity is going to equal, well, area is 0.001 square meters times the velocity, which is 4.43 meters per second. If I multiply meters squared by meters per second, I get meters cubed per second. That's cubic meters per second. So I get 0.00443 cubic meters per second. So if I ask for flow rate in terms of cubic meters per second, I'd be done. But I don't want cubic meters per second, I want kilograms per second. So I need to find a way to convert from cubic meters per second to kilograms per second. Here's my conversion right here. Density is mass over volume. So mass is going to equal density times volume. There's how I can convert from a volume to a mass. I just multiply it by the density. So if I multiply this by the density, multiply by 1,000, move it over 3 places, I get that it's 4.43 kilograms per second. Last question, what's the Reynolds number? Is this turbulent? Like, how turbulent is this? Well, the equation for Reynolds number is just R equals velocity times radius times density divided by viscosity. Well, what do we know? We know the velocity is 4.43. We know the radius is 0.018. We know the density is 1,000. Now the viscosity of water, but water always has some really cool numbers, like even numbers, because a lot of stuff is based off of water, like volume and stuff. So, but viscosity for water is about 0.001. So, if I do that, I'm going to get a pretty big number. I get, let's see, a number of 79,000, just shy of 80,000. Now Reynolds number is unitless. 80,000, so this is pretty turbulent. It's going to come out of there like glub, 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 kind of random. So, because 80,000 is a pretty big number. Typically, like they say, like anything over a couple thousand is turbulent. So like 4,000 is like the maximum that a smooth flow, like laminar flow, would go to. 2 to 4,000 in that range. They would just say that's kind of like the borderline of when things are starting to get chaotic. This is pretty chaotic. 80,000 is quite a bit bigger than 4,000. All right, so there's fluid dynamics. Yay.